Here we are with Taylor's theorem, and we would like to give a proof here. In fact, this proof is non-standard in the sense that I do not believe that you will find it in any standard literature, but I think it delivers a very key and fundamental idea, and that is the following. That if you start with a function f, and you would like to approximate it using polynomials, for example, a polynomial of degree 1 or a polynomial of degree 2 or a polynomial of degree 3 or a polynomial of degree 4. The higher the polynomial you have, the closer and the more accurate your function will look like. So we can fit our Taylor polynomials, or let's say they're not Taylor just yet because we're trying to prove that. We're fitting our polynomials to the function. And the question is, how do you fit a polynomial to a function? And what differentiates one polynomial from the other? And the answer for that simply is the coefficients. The coefficients tell you this is a polynomial and this is another polynomial. And so I will proceed with the assumption, and this is an assumption, that we can write f of x as an infinite polynomial of the following form. It is infinite because we would like to look at some sort of infinite polynomial setup, and it is centered at b. That is very important, which means that if I plug in x is equal to b, I will get C0, because this term will cancel, and that term will cancel, and that term will cancel, and so on and so forth. So let me write this now. If I plug in f of b, I get C0 plus C1 times x, b minus b plus C2 b minus b squared, and so on and so forth. And well, this is great, right? Because then this is equal to 0, this is equal to 0, and then I can write down that C0, my zeroth coefficient, is going to be equal to f of b. Now we need a trick if we would like to find, for example, C1. How do we find C1? Can we simply plug in b? It doesn't work. It's not going to work. What can we do about it? And this is a calculus class, so the answer is much closer than you think. We will take the derivative of b. The derivative of b is going to be C1 plus C2 times 2 times x minus b plus 3 times C3 times x minus b squared, and so on and so forth. And now I can plug in b. So that is the trick here. You see the trick? That's a very nice trick. So if I plug in f of b here, this is 0 and that is 0. And I simply get the following equation. So C1 is equal to f of b. Now, is C2 also going to be equal to f of b? Well, not f of b, my apologies, f prime of b. Is for example, C2 going to be equal to f double prime of b? That's a question for you. Maybe think about it. Maybe try to pause the video and compute f double prime of b. Well, let's see. So f double prime of b means that we'll differentiate this thing twice. So this will die off, and that will die off. This will survive. This will survive. Because if I take the second derivative of this thing, well, let's say I just take the first derivative of this thing. The first derivative is, well, you drop down the 2, and you take away 1 from the power. Then you take the derivative again. Then this thing goes away, and you're left with 2 times C2 is equal to f double prime of b. And now you're wondering why I didn't write the remaining terms. Well, it's just because I'm lazy. It doesn't have anything to do with it. But the next term is going to be, well, it's going to be the derivative of that term. So it's going to be 3 times 2 times C3 times x minus b to the power of 1. And since all the other terms will have x minus b to the power of something in their in their product, then plugging in b will always cancel out these other terms, which means I could write C2 as f double prime of b, but this time we'll divide by 2. And from here, I think we see a pattern. So it seems that if we take the nth derivative and we plug in b, we get something that contains C2. What is this something? Is it n? It's not n, right? Because it can be n. If it's n, then it's 0 times f of b. It doesn't work. It works from here. It works from there. So we have to figure out what's going on, and maybe what will help us to find out what's going on is if we look at one more example. I hope you've already seen the pattern, but if you haven't, that's fine. I'll do one more for you. So triple third derivative of f of x at b is going to be the following. It's going to be this expression taking the derivative. So we get 3 times 2 times C3, and the derivative of this is 1. 3 times 2 times 1 times C3 plus something that has x minus b to the power of 1. And so that's the next term, basically. If you want me to compute it, I can compute it for you, but it's not meaningful. Like every single time we get this thing, and then there's something that has power 1, and then something that has power 2, and so on and so forth. So something that has power 2, and so on and so forth. And so if we plug in b, this becomes 0. I've made a horrendous mistake, which is not plugging in b here. Please forgive me. Thank you. Now I don't have to redo this. It's the second time already. So so here I'm at f triple prime of b, and it seems to give me the following. So if I solve for C3, I'll get f triple prime of b, so the third derivative, divided by 3 times 2. What's going on here? What's in common? So this is 1, this is 0. Okay. Maybe I shouldn't have written that. This is still 1. But it gives you a hint to what's going to happen right now, because here's what's going to happen. I just want to make sure everything is in frame. And now it is. So here's what's happening. This is 0 factorial, and this is 1 factorial, and this is 2 factorial, and this is 3 factorial. And you should agree with me on this. So what's going on here really is you have n factorial times Cn. And you can prove this by induction, if you would like, and or simply differentiate this term n times like we did, you always get the n factorial next to the Cn, which means that my Cn will always be Fn at b divided by n factorial. And is this all we need? Let's see. Well, yes, because we assumed that we can describe this f in terms of some polynomial that's centered at b, and we have found the coefficients to be exactly as supplied in the theorem. And by this, it simply means that we have found the coefficients. And if the coefficients match here, then it is indeed true that we may be able to approximate the behavior of f of x using its derivatives. So that is just simply amazing. So we have fn of b divided by n factorial. Maybe I'll use k to be consistent with the theorem, but in principle, this works perfectly fine. So we have found a formula for describing the coefficients of this polynomial, and it's always determined by the derivatives of the function. And I think that's very powerful, because sometimes you look at things and you take them for granted, but this is a very special case where you shouldn't, and I'm glad you've stayed for all this time to hear about it. And now you know one more proof or one more way of arguing for these weird factorials and these weird derivatives. And now you know how this goes. So I hope not to see you here again if the question is related to a Taylor polynomial or something similar, because I assume that you've acquired the relevant knowledge. Otherwise, you'll have to hear me, listen to me blabber about some mathematical nonsense that's practically irrelevant in whatever you do outside of this class. But here we are.